The nitrifying bacteria. The nitrifying bacteria are those which have the power to form nitrate. In the following brief discussion of this subject, we include at least 3 species of bacteria, which by their combined or successive action have the power to transform organic nitrogen into nitrate. Nitrogen, which is a suitable form of nitrogen for plant. For the exact information which we now have regarding the nitrifying bacteria, we are indebted to the researches of Pasteur and Schleusing and Muntz of France, Winogradsky of Russia, Warrington of Englers. The nitrogen in the soil is almost entirely in organic compounds. That is, the nitrogen, which is a gas in the free or uncombined state, is united or combined with other elements, notably with carbon, hydrogen, and oxygen in the form of partially vegetable or organic matter. By organic matter, we mean matter which has been formed by the growth of some organism, either plant or animal as grass or flesh. Plants cannot use the free nitrogen of the air as plant food. Neither can they use the organic compounds of nitrogen which occur in the soil. There are at least 3 different kinds of bacteria, and also 3 different steps or stages involved in the process of nitrification, the nitrogen being changed from the organic compounds first into the ammonia form, second into the nitrite form, and third into the nitrate form. During the process, the nitrogen is separated from the carbon and other elements composing the insoluble organic matter, and is united or combined with oxygen and some alkaline element, as calcium. Form the soluble nitrates such as calcium nitrate, which is one of the most suitable compounds of nitrogen for plant food. Calcium is the alkaline element contained in lime or limestone. The name calcium nitrate indicates just what elements this compound contains, namely calcium, nitrogen, and oxygen. In the names of compounds, the ending ate always means oxygen. This is the general process of nitrification in which the nitrifying bacteria transform or transfer the nitrogen from insoluble organic compounds into soluble compounds in which it may serve as available. The nitrate which is thus formed may be calcium nitrate or magnesium nitrate or potassium nitrate or even sodium nitrate, depending upon which of these alkaline elements is present the most suitable. If no alkaline element is present in available form, then no nitrates can be made in the soil. One of the reasons for applying ground limestone to soils which are deficient in lime is to furnish the element calcium in suitable form for the formation of nitrates in the process of nitrification. Ground limestone is calcium carbonate, CO3, a compound containing 1 atom of calcium, T, 1 atom of carbon, C, and 3 atoms of oxygen. This is the same form of lime which is contained naturally in limestone soils which are noted for their great productiveness, and is generally the most economical form of lime to use for correcting soil acidity and promoting nitrification. In the process of nitrification, that is in the formation of nitrates, there is required not only the presence of calcium or some other alkaline element in suitable form, but also a good supply of the element oxygen. For calcium nitrate, CaO3 contains 1 atom of calcium, Te, 2 atoms of nitrogen, and 2 and 6 atoms of oxygen in each molecule as indicated in the formula CaO3. Magnesium nitrate, MgNO3, potassium nitrate, KNO3. K is from the Latin word kalium, which means potassium, and all other nitrates also contain oxygen. The supply of oxygen for the formation of nitrates in the soil comes from the air, which consists of about 20% oxygen, 78% nitrogen, and 2% of other elements. Compounds as argon, carbon dioxide, CO2, water vapor, H2O, etc. One of the important effects of cultivation or tillage is that it permits the air more freely to enter the soil and thus promotes the nitrogen-gathering bacteria. As stated above, the nitrogen naturally in the soil is contained almost entirely in the organic matter. Any process which tends to decompose or destroy this organic matter, such as nitrification or other forms of oxidation, will also tend to reduce the total stock of nitrogen in the soil. Because of this fact, the matter of restoring nitrogen to the soil becomes of very great importance. Of course, a part of the nitrogen removed in crops may be returned in the manure produced on the farm. And nitrogen may also be bought in markets in such forms as sodium nitrate, containing 16% of nitrogen, ammonium sulfate, containing 20% of nitrogen, and dried blood containing 12 to 15% nitrogen. When we bear in mind that such commercial nitrogen costs about 15 cents a pound, and that 1 bushel of corn contains about 1 pound of nitrogen, it will be seen at once that the purchase of nitrogen cannot be considered practicable in general. Farming, although in market gardening and in some other kinds of intensive agriculture, commercial nitrogen can often be used with very marked profit. Nitrogen is removed from the soil not only in the crops grown, but also and frequently in larger amounts per annum in the drainage waters and in some other ways as by denitrification and by the blowing and washing of the surface soil. Professor Snyder of the Minnesota Experiment Station has shown that during a series of years the total loss of nitrogen from some Minnesota soils in some cases amounts to several times the amount actually used in the crops. Considering all of these facts, and the additional facts that there are about 75 million pounds of atmospheric nitrogen resting upon every acre of land, and that it is possible to obtain unlimited quantities of nitrogen from the air for use of farm crops and at very small cost, the inevitable conclusion is that the inexhaustible supply of nitrogen in the air is the store from which we must draw to maintain a sufficient amount of this element in the soil for the most profitable crop yields. It is often stated that leguminous plants, such as clover, have power to free nitrogen from the air. This is not strictly true. Red clover, for example, has no power in itself to get nitrogen from the air. It is true, however, that the microscopic organisms which commonly live in tubercles upon the roots of the clover plant do have the power to take free nitrogen from the air and cause it to unite with other elements to form compounds suitable for plant food. The clover plant then draws upon this combined nitrogen in the root tubercles and makes use of it in its own growth, both in the tops and in the roots of the plant. These nitrogen-gathering bacteria live in tubercles upon the roots of various leguminous plants, such as red clover, white clover, alfalfa, sweet clover, cowpeas, soybeans, field peas, garden peas, field and garden beans, etc. These tubercles vary in size from a pinhead to a pea, varying with different kinds of plants, being especially small upon some of the clovers and very large upon cowpeas. The tubercles are, of course, easily seen with the eye, but the tubercle is only the home of bacteria, somewhat as the ball upon the willow twig is the home of the insects within. The bacteria themselves are far too small to be seen with the unaided eye, although they can be seen by means of most powerful microscope. Several million bacteria may inhabit a single tubercle. It is not necessary to see the bacteria, because if we find the tubercles upon the roots of the plant, we know the bacteria are present within, as otherwise the tubercle would not be formed. Although the plant itself, as clover, for example, has no power to feed upon the free or uncombined nitrogen in the air, yet these nitrogen-gathering bacteria do have the power to absorb the free nitrogen and cause it to combine with other elements, forming nitrates or other compounds which are suitable forms of nitrogen for plant food. It has also been demonstrated that, as a rule, there are different species of nitrogen-gathering bacteria for markedly different species of leguminous plants. Thus, we have one kind of bacteria for red clover, another kind for cowpeas, another kind for soybeans, and still a different kind for alfalfa. The red clover bacteria. That clover has no power in itself to gather atmospheric nitrogen, and the bacteria do have power to feed the clover plant nitrogen gathered from the air is very easy to demonstrate. It is one of the regular laboratory practices of the students in soil fertility in the agricultural college to make this demonstration. Plate 1 is an illustration of such student work. The 2 pots which are shown were provided with all elements of plant food, excepting the one element nitrogen. Thus far, the 2 pots are exactly alike. Each contains no nitrogen as indicated by the label, no N. Each pot is planted with the same number of red clover seeds. To the right-hand pot, however, some bacteria were added, while none were added to the left-hand pot. These bacteria were obtained by taking about 1 pound of soil from a clover field where abundance of tubercles were found on the clover roots, adding this soil to about 1 quart of pure water, shaking for a few minutes, allowing the soil to settle, then taking a small quantity of almost clear solution and adding it to the pot which we wish to inoculate with the red clover bacteria. Aside from the addition of these microscopic bacteria to the right-hand pot, these two pots were treated exactly alike throughout the experiment. It will be plainly seen that where the bacteria were added, the clover was furnished with sufficient nitrogen to make a strong and luxuriant growth, while without the bacteria, the clover, in the left-hand pot, only germinated and made what little growth it could with the small amount of nitrogen contained in the seed. This result is the difference between success and failure of the clover crop. In general, the clover bacteria are well distributed over the northern and central part of Illinois, but we now have some very strong evidence that they are not distributed in some soils of large in southern Illinois. There is also some evidence that they were not originally present even in the soils where they are now found in great abundance, and furthermore, it seems very probable that these bacteria may cease to live in a soil where they have once been present, provided clover is not grown on the land for several years. It will help us to understand this matter if we bear in mind that the home of these bacteria is the tubercle upon the clover root. It is quite evident that they will continue to live upon the decaying tubercles or roots for 3 or 4 years after the clover plant has been killed. On the other hand, we have some notable evidence that the bacteria do not continue to live in a soil after 5 or 6 years continuous cropping with absolutely no clover growing on land during. It is a simple matter for anyone to determine whether the bacteria are present or not, for the tubercles which are formed if the bacteria are present are plainly seen attached to small roots. They look somewhat like miniature potatoes, varying in size from pinheads on clover to peas on soybeans or cowpeas. See plates 2 and 4. It is important to remember that bacteria live in the soil and not in the seed. When clover is cut for seed, it is frequently left to lie upon the ground until the straw becomes half rotten and very dirty. And consequently, when it is threshed, it practically always happens that there is at least some small amount of dust and dirt taken with the seed. This dirt is almost sure to carry with it some bacteria from the soil. If these few bacteria are scattered with the clover seed when it is sowed, they will inoculate at least a few plants, and if they are allowed to multiply on these plants, and especially if the same field is repeatedly seeded with clover, the soil will ultimately become thoroughly infected with the clover bacteria. Of course, they may be carried from one part of the farm to another, or even from one farm to another by various agencies as dust or wind storms, surface drainage or flood waters, manure made from clover hay, implements used in cultivating the soil, etc. Many of the older farmers of Illinois have stated to the writer that when this country was very new, it was commonly found difficult to get a catch of clover on new land. After a good catch was once gotten, then it was easier to get clover to grow on that land the next time. There was a saying among the farmers that clover would not do well until they got the wild nature out of the land. Their final success was undoubtedly due not to getting anything out of the land, but rather to getting the bacteria into the land. Several Illinois farmers have reported some remarkable results from very light applications of the clover chaff or straw obtained whole in clover, and its beneficial effect on clover on land, where it was otherwise difficult to get a catch. There is a somewhat general belief among farmers of long experience that clover straw or chaff has some special value in getting a catch of clover. Aside from its value as manure or for the seed, which it sometimes Manager F. A. Warner of the Sibley Estate, Ford County, recently stated to the writer that they had very great difficulty to get clover to grow when they first began growing clover on that large estate some 6 or 8 years ago. Although after a good crop was once secured, they rarely had any further difficulty in getting a catch of clover on the same land. On the common gray prairie soil of the lower Illinois and glaciations, in southern Illinois, the commonest type of soil in more than 20 counties, practically no red clover is grown. In the spring of 1903, we seeded red clover on that type of soil in 3 places, namely on the University of Illinois soil experiment fields near Edgewood, Effingham County near Du Bois, Washington County, and near Cutler. On certain plots, the soil acidity had been corrected with lime, and an abundant supply of phosphorus in bone meal had been provided, potassium also having been added on some plots. These fields were carefully examined the latter part of June, and at Cutler and Boise the clover was found to be dying, and no tubercles could be found upon the clover roots, although on the clover which had been seeded at about the same time on the university fields at Urbana, the root tubercles were found in great abundance. At Edgewood a few tubercles were found, and the clover appeared to be growing fairly well. Infected red clover soil was once procured and scattered over the fields at Edgewood, Du Bois, and Cutler, but it was evidently too late to be of any marked benefit. At Cutler and Du Bois the clover was a complete failure. It will be tried again next year. At Edgewood it continued to grow fairly well, and its progress next season, 1904, will be watched with much interest. It should be stated that the experiment station has been growing clover for several years with varying degrees of failure on land adjoining the present clover field at Edgewood. It is possible that this year's apparent success from the start is due in part at least to the bacteria, which have been incidentally introduced and multiplied year after year and scattered over the adjoining land by wind and dust storm. Before the close of the season, the tubercles developed in abundance on the roots of the clover at Edgewood. An experience reported by Professor Herbert W. Mumford of the Animal Husbandry Department of this university will be of interest and value in this connection. Professor Mumford commonly grows clover in his rotations on his own private farm, but he states that at one time one particular field was cropped continuously with timothy, oats, and corn for some 6 years or more without any clover. It was then again seeded to clover, but the crop made a complete failure, although on other land where clover had been grown more recently, a successful clover crop was grown from the same kind of seed. Seeded about the same. The following year, this particular field was again seeded to clover. This time the catch was not a total failure, but it was too poor to save, and it was plowed up and the land again seeded to clover the next year, and an excellent catch of clover resulted. After this, clover was frequently grown on this field, and no special difficulty was had in getting good crops. While the failure of clover may often be due to drought, and in some places due to soil acidity, lack of lime, and sometimes even due to an insufficient supply of available phosphorus or of potassium, we now know with certainty that it sometimes fails because of the absence of the nitrogen-gathering bacteria, especially on land which has never grown clover, and probably also on land which has not grown it. We should always remember that the bacteria do not thrive in strongly acid soils, even though they may sometimes live in such soils and perhaps produce some tubercles upon the roots of certain hardy, strong-growing legumes like cowpeas. Nevertheless, we are obtaining some strong evidence that in such acid soils they have but little power to gather nitrogen from the air. That ground limestone is the most economical and satisfactory material to use in correcting the acidity of soils is strongly indicated by the information we have thus far obtained. On the upland prairie soils of the lower Illinois and glaciation, where red clover has never been grown successfully, largely because of the acidity of the soil, it will undoubtedly be helpful, profitable not only to correct the acidity of the soil with ground limestone, but also to secure infected soil from some field of timberland or bottomland where red clover is growing, well provided. with root tubercles and inoculate the field with. This soil should be collected to a depth of 3 or 4 inches and scattered over the prairie land at the rate of a few £100 per acre at the time the clover is seeded or before. The cowpea bacteria are already quite widely distributed in southern Illinois, especially where this crop has been grown for several years, but they are not common in the soils of other parts of the state. It is doubtful, however, if it is necessary or even worthwhile to take the trouble to inoculate soil for cowpeas. Some few tubercles almost invariably develop on cowpea roots the first year they are seeded, even where they have never been grown before, and if seeded the second year on the same land the plants are usually abundantly provided with root tubercles. Just why the cowpea bacteria develop so rapidly without special inoculation is not definitely known. It may be that the same bacteria also live on some other leguminous plant which is more or less widely distributed over the state, but it seems more likely that the bacteria are brought with the seed. As a matter of fact, the cowpea harvest is usually dirty. This is an annual plant, and consequently the crop is grown on recently plowed land and is sometimes cultivated during the season. Cowpeas are commonly harvested with a mowing machine and then raked up on the loose ground. When they are threshed, more or less dirt remains with the seed. Furthermore, the seed coats are not infrequently cracked, thus providing an excellent place for the lodgement of particles of soil. Whether it would be profitable to inoculate the land for cowpeas would depend very largely upon the difficulty or cost of obtaining the infected material. If soil thoroughly infected with the cowpea bacteria can be scattered over the land at the rate of about £2,000 to the acre at a cost of $100 or less per ton, it might prove profitable. It is doubtful if a light application of 100 or 200 pounds would produce any very marked effect in the yield the first season. After the soil becomes well infected, the cowpeas then obtain much nitrogen from the air, and the yield of the cowpeas is likely to be largely increased. Of course, there is no fixation of atmospheric nitrogen if there are no tubercles on the roots. In 1902, several plots of cowpeas were seeded on the soil experiment field at the university. One of those plots had become thoroughly infected with the cowpea bacteria because being so situated that more or less surface drainage water flowed over it from an adjacent field upon which cowpeas had been grown for 3 successive years. Another plot, 4.8, owing to a slightly different situation, had not become infected. The 2 plots were seeded in July after a crop of oats had been removed from the land. Within 3 weeks after seeding, numerous root tubercles could be found on the plants on the infected plot. Later on, 10 average consecutive plants were taken up as completely as possible, and 412 tubercles were found on the roots, making an average of more than 40 tubercles to the plant. On plot 4-8, only an occasional plant was found infected, and such plants would usually have only a single large tubercle on their roots. 10 average plants not infected were collected from plot 4-8 for comparison with the 10 infected plants from plot. The results clearly show the very great value of the nitrogen-gathering bacteria in growing cowpeas. In each of the separate trials A, B, and C, the infected plants contained about twice as much total dry matter as the plants not infected. The infected plants also contained a much higher percent of nitrogen than the plants not infected. The infected plants containing 4.09 to 4.33% per tops and 145 to 153% in the roots, while those not infected contained only 2.32 to 2.69% in the tops and 88% in the roots. Besides this, the tubercles on the infected plants contain 76 to 6.5% of nitrogen. In these young and rapidly growing plants, the tubercles are much richer in nitrogen than any other part of the plant. It should be stated that as the plants approach maturity, the nitrogen is largely absorbed from the tubercles and stored in the tops and roots. At the time these plants were taken up, the tubercles actually contained more nitrogen than the roots. The infected plants contain nearly 4 times as much nitrogen as the plants not infected, and about 3/4 of the total nitrogen in the infected plants was obtained from the air. The roots and tubercles of the infected plants contain 6 to 7 times as much nitrogen as the roots of the plants not infected. The soybean bacteria. Soybean bacteria are evidently much less likely to be carried with the seed than are the cowpea bacteria. The soybean plant grows more erectly than the cowpea, and the crop is quite commonly harvested with a self-binder which keeps it quite free from dirt. The soybean seed is nearly round and smooth, and the seed coat is not commonly cracked. These facts may explain why the soy seed carries so few bacteria as compared with cowpeas. On one of the soil experiment fields on the university farm at Urbana, where soybeans have been grown for 3 years, no tubercles could be found on the plants either the first or second year. Only an occasional plant with tubercles could be found the third year. In 1902, a series of plots, some of which had been treated in different ways with applications of limestone phosphorus and potassium, were seeded with soybeans. No tubercles could be found at any time during the season on the soybeans growing on any of different plots. In 1903, the same plots were again seeded to soybeans, and at the same time part of each plot was inoculated with infected soybean soil drilled in with the seed at the rate of about 500 pounds infected soil to the acre. When the plants were only a few weeks old, tubercles were to be found upon many plants growing where the infected soil had been applied, and before the close of the season at least half of these plants in the inoculated part of the field had one or more tubercles upon their roots, and some plants could be found whose roots were abundantly provided with tubercles. On the uninoculated part of the field, soybean plants were examined probably 50 times during the season, several plants being taken up each time, but not a single tubercle was found at any time. Notwithstanding that this was the second crop of soybeans upon this soil. Of course, the inoculated part of the field did not become sufficiently infected to markedly benefit the 1903 crop, but it is planned to grow soybeans upon this field again in 1904 when the bacteria will doubtless have multiplied sufficiently to produce marked results in the growth of the crop. From these and from other somewhat similar experiments, it is concluded that as a rule soybeans should be inoculated when they are first seeded, and that they should then be grown a second year upon the same. If soybeans are afterward grown upon this land once in every 3 or 4 years, the soil will doubtless remain well infected with the soybean bacteria. It is believed that 100 pounds of infected soybean soil per acre will be sufficient to produce a thorough infection the second year, and it is improbable that 1 ton of infected soil per acre would produce a thorough inoculation the first season. 1 ton is only 20 times 100 pounds, while 1 tubercle, which will be produced during a single season from a single bacterium, may contain many million bacteria. Thus it will be seen that it will be more economical to inoculate rather lightly and allow the bacteria to multiply themselves rather than to inoculate heavily at great expense. It may be stated that the infected soybean soil used in these experiments was obtained from Mr. A. Hinckley of Boise, Illinois, who has been growing soybeans on the same land for many years. It has become well infected. Mr. Hinckley has consented to furnish infected soybean soil so far as he is able to do without serious interference with his regular work to anyone who may desire it at a price which will cover his expense. This will probably amount to about $1 for the first 100 pounds and 50 cents for each additional 100 pounds, in the shipment including the cost of bags, the purchaser to pay freight from Boise Station, which is located in Washington County, Illinois, on the Illinois Central Railroad. The alfalfa and sweet clover bacteria. That soil inoculation with alfalfa bacteria is commonly of very great value in growing alfalfa has been shown very conclusively by the investigations reported in Bulletin 76 alfalfa on Illinois soil. In some places, however, inoculation was found to be unnecessary. A careful and extensive investigation of alfalfa growing in different parts of Illinois revealed the fact, as stated in Bulletin 76, that the alfalfa bacteria are certainly present in some places in the state, while in most other places they are certainly not present in sufficient number to become of appreciable assistance to the alfalfa within 3 or 4 years. And the question naturally arises how it happens that some fields are already infected while others are not. It was suggested in that bulletin that the alfalfa bacteria may live on some other plants besides alfalfa. One of these plants is native or has been introduced in certain sections of the state. It was also suggested that a few bacteria are always carried with alfalfa seed, and that if the alfalfa is grown continuously or repeatedly in any place, the soil will finally become thoroughly infected, and the bacteria will then be carried by floodwaters, dust storms, etc., over adjoining fields, and possibly for long distances, especially along river valleys. This latter suggestion was known to be a fact at the time it was written, and subsequent investigations have furnished conclusive proof that the alfalfa bacteria do live upon other plant, namely the ordinary sweet clover, Meloba. This is a rank-growing leguminous plant, frequently reaching a height of 4 to 6 feet. When young it markedly resembles alfalfa, but it can easily be distinguished by its characteristic odor when cut or bruised, as by rubbing between the hands. As the sweet clover approaches maturity, it differs very much from alfalfa. The sweet clover grows very tall and usually branches from a main stem. It has white flowers. There is also a less common yellow variety, and the seeds are borne in small round pods, usually containing only 1 or 2 seeds each, arranged on long slender spikes, spike-bearing pods. The alfalfa commonly grows about 2.5 feet high, with many stems growing from the crown of the root, especially after it is 2 or 3 years old. It bears purple flowers and peculiar spiral-shaped seed pods. Sweet clover is a biennial plant dying after reaching maturity, which commonly occurs the second year of its growth. Like many other biennial plants, it probably often lives more than 2 years if not allowed to produce seed. Alfalfa is a perennial plant, and it is said that there are alfalfa fields which have been cut annually for more than 50 years without reseeding. The similarity of alfalfa and sweet clover when young, and also the similarity of the tubercles formed on the roots of each, have long been noticed, and the possibility of the same bacteria living upon both plants has already been suggested in the agricultural press. During the season of 1903, the writer spent some time in the northern part of Illinois in connection with the general and detailed surveys of Illinois soil. Many new fields of alfalfa were observed, and they were carefully examined for root tubercles. In Winnebago County, where sweet clover is very prevalent along roadsides and waste places, it was noted the abundance of root tubercles on the alfalfa plants seemed to be closely related to the presence of sweet clover in the vicinity. Strongly in the bacteria which live upon sweet clover were also at home upon the alfalfa roots. These indications were strengthened by further investigations in Lake County, especially upon the Fowler Farm near Lake Villa, where a field of alfalfa seeded last spring without artificial inoculation was found to be thoroughly infected with the bacteria and growing vigorously with a good dark green color. This field had a few sweet clover plants growing in it, and the borders of the field were covered with sweet clover. Other fields of alfalfa seeded in the neighborhood at the same time, but upon soils where sweet clover had not grown nearby, were apparently complete failures, many of the plants having died and most of those still living being only a few inches high, very weak and yellow or pale green color. From these investigations, we thus have conclusive evidence that infected sweet clover soil can be used for the inoculation of alfalfa fields, the bacteria of the two plants acting the same. The infected soil may be obtained from any place where the sweet clover is found with abundance of tubercles on its roots. The soil may be collected to a depth of 3 or 4 inches and scattered over the alfalfa field at the rate of 100 pounds or more to the acre. It is well to scatter the infected soil at about the time the alfalfa is seeded, and harrow it in with the alfalfa seed, although may be applied some days or even some weeks before seeding time. And probably it would be all right to apply the infected soil the fall before, for it is known that the bacteria will live in soil for several months, even though the soil be placed in sacks. A light tribe. Investigations have shown that 100 pounds of thoroughly infected soil to the acre is sufficient to produce a very satisfactory inoculation within 1 year from the time it's applied. Of course, somewhat heavier applications may well be made if it can be done at small expense. The infected soil need not be applied with any high degree of uniformity, but special care should be taken that the higher places and watersheds are not missed in scattering it over the field. If a few square yards, or even square rods, should be missed on the slopes or lower land, it would make but little difference as the bacteria will be washed over such places from the higher land. After the soil becomes somewhat dry, it is easily scattered by hand from the wagon or from a sack which one can carry. Sometimes it is applied by means of an end-gate seeder or a fertilizer drill, or it could be spread by a manure spreader with an application of manure. The question naturally arises whether there is not danger of getting some sweet clover seed, the infected sweet clover soil, and thus of getting sweet clover mixed with the alfalfa in the field. In the writer's opinion, there is little or nothing to fear in this matter. In the first place, the amount of sweet clover seed thus obtained would be very small, probably none at all, if one were careful to scrape off the vegetable matter and perhaps a hatch of earth. Before collecting the infected soil, most of the bacteria are probably between 1/2 inch and 6 inches in depth, as most of the tubercles develop and decay between those depths. Second, it is doubtful if a small amount of sweet clover hay would lessen the value of alfalfa hay in the least, for stock frequently eats small amounts of sweet clover of their own choice, even when it is nearly mature, and if it is cut while still quite immature and tender, it makes quite satisfactory hay, so much so that in some sections of the United States, particularly in the South, sweet clover is regularly seeded on fields and cut for hay, and it is found to be a valuable and very nutritious feed, the livestock eating it in large quantities and with apparent relish after they have acquired a taste for it. Third, sweet clover is not known as a bad weed in the fields or meadows, even where it has been a common roadside plant for many years, being naturally a biennial plant if it were cut down every 5 or 6 weeks. As we commonly cut alfalfa during the season, it would almost certainly die out after a few years, while alfalfa, a perennial plant, would continue to live. Only one instance has come to the writer's attention where alfalfa has been growing for several years with sweet clover growing in the field or fence rows beside it. This is on the farm of Mr. D.S. Mayhew of Mercer County, Illinois, who writes as follows regarding the matter. Will say that the sweet clover has made no headway in my meadow, as it did not go to seed, on account of my cutting it so often. The sweet clover got into the alfalfa in the seed when I sowed it. I do not think it will do any harm in a meadow, but I believe it would do harm in a pasture if it wasn't cut down, as stock will not eat the sweet clover. Of course, if sweet clover should get into the field and persist in growing, and if it were found to injure the alfalfa appreciably or markedly, we can always resort to plowing the ground up and growing corn or other crops, thus obtaining some benefit from the leguminous crop for its fertilizing value, and at the same time completely eradicating the sweet clover, but leaving the soil well infected with alfalfa bacteria ready to serve in case alfalfa should be again seeded within a few years. In general agriculture in Illinois, whether it be grain farming or ordinary livestock farming, the growing of legumes is absolutely essential as a part of any economic system which shall maintain fertility of the soil. And for the successful growing of legumes, the presence and assistance of the proper species of nitrogen-gathering bacteria are also absolutely essential. These facts being granted, it certainly follows that when sowing a legume on land, where the same legume has never been grown before, or perhaps where it has not been successfully grown within recent years, we should always consider the matter of inoculation, unless there is good reason to believe that the soil has been inoculated by the washing from other lying land where these bacteria are known to be present, or by applications of manure made from that legume, or by some other such incidental means, or unless there is evidence that the bacteria are carried with the seed in sufficient quantity to effect a satisfactory inoculation, as appears to be the case with the cowpea. Then we should inoculate the soil directly with the specific bacteria required by legume which we desire. While some Illinois soils are becoming deficient in phosphorus and in lime, especially in the southern part of the state, and while phosphorus and ground limestone can be applied to such soils with marked benefit and profit, especially for the growing of legumes, there is abundant evidence that one of the dominant causes for the failure or unsatisfactory growth of some of our most valuable legumes, and on some soils the sole cause of failure, is the absence of the proper nitrogen-gathering bacteria. There is no reason to believe that any of the different species of nitrogen-gathering bacteria will live in the soil for more than a few years in the entire absence of any legume upon which they naturally live, and the accumulating evidence strongly indicates that the bacteria which are present in places in our soils, such as the red clover bacteria now found abundantly in many places in state, especially in northern and central Illinois, the cowpea bacteria more common in southern Illinois, and the alfalfa or sweet clover bacteria, which are becoming prevalent in some sections, that all these have been and are being gradually introduced and extended almost entirely by mere chance. Of course, if the wagon wheel, which carries the mud along the road, carries that sweet clover seed from one place to another, it may also carry the sweet clover bacteria which live on the sweet clover